All right, so today we're going to talk about using the idea of derivatives to kind of be able to tell what uh, function as far as the graph looks like, and the different attributes of functions. Now, if you remember, in pre-calculus we were sketching graphs of polynomial functions or other types of functions, and we were saying that they're about 90% accurate. Now what calculus does is it's going to allow us in a simpler way of sketching the graphs of any type of a function to pretty much 100% of accuracy. So calculus once again kind of comes to the rescue when it comes to like dealing with complicated functions or everything that looks complicated, but kind of calculus helps simplify it. So the goal today is the following: is to use the first and second derivatives of a function to help determine its behavior. And keep in mind that we will kind of continue on with this. So today we're breaking up section 3 into 2 days. So today our main focus will be the first derivative, and then tomorrow we'll talk about what the second derivative does. And then eventually in the upcoming sections we'll kind of put all of these pieces together, and then we'll kind of produce a graph that's 100% accurate to what a function should look like. So technically speaking, the graph that we draw using calculus will match up exactly to the graphing calculators that you've been using, for example. Okay, so let's go into what f prime determines about our function. Now remember, we're using information about f prime, or we're finding the derivative of f, which is f prime, and then based on f prime, we'll be able to get information about f. Okay, so let's go ahead and talk about the increasing decreasing test. And the increasing decreasing test says the following. It's two statements. It says if f prime of x is greater than 0, and in fact, think of it this way: on an interval. So what do we know about f prime? See, f prime is in one way of describing f prime, which there are many ways we could describe it. This represents kind of like the slope of the tangent line. Okay, so if f prime is positive, what does that mean about my slopes? My slopes are positive, which in other words, if the slopes of my tangents to a curve to f are positive, then what does that mean about f in terms of increasing or decreasing? And if you said that if f prime is positive, that means f itself is increasing on that interval, then you are correct. So what we could say is that then f is increasing on that interval. Okay, so think of it this way. Whenever f prime is positive, what does that mean about f? It just means f at that point, or at that x value, is increasing. Okay, so what if f prime is less than 0? And I'm sure you've already said that f is decreasing. So if the derivative of f is negative on an interval, then f is decreasing on that interval. Okay, so if you think about it, all we really care about is kind of the sign of f prime. Is f prime positive or negative? And then we'll be able to tell if the function f itself is increasing or decreasing. So let's look at an example. Let's look at our first example. Say find where the function f of x equals to 3x to the fourth minus 4x cubed minus 12x squared plus 5. So we're finding where this function is increasing and decreasing. Okay, so as always, we care about the derivative because remember the derivative tells us where a function is increasing or decreasing. And I want to make a sign chart for this. You guys have seen me make sign charts before when it comes to finding domains or when it comes to the velocity and acceleration problems. Is an object moving upwards, downwards? Well, it depends if the velocity is positive or negative. So we're going to do the same thing here. We want to figure out when the derivative is positive and negative. Now, to be able to do that, the first thing we need to do is we need to find the derivative and its zeros. Because the zeros are going to help me kind of figure out how to break these up, right? Because remember, the way we're going to find the zeros is hopefully by factoring, okay? So let's do this now. So the derivative, f prime of x, will be 12x cubed minus 12x squared minus 24x. Okay, and now what I want to do is I want to set this equal to 0. So 12x cubed minus 12x squared minus 24x equals to 0. And remember, the zeros are the places where I'm going to basically, where my function potentially changes from positive to negative and so on. So let's factor. What could I factor from this? I could already see I could factor out of 12x. And that leaves me with an x squared minus x minus 2. And I could see I could factor this quadratic even more. So 12x times x minus 2 times x plus 1. And so I found the zeros. This is equal to 0 at 0, 2, and negative 1. So what I'm going to do is I'm going to grab these factors. And using those factors, I'm going to make a sign chart. And the sign chart is going to tell me where f prime is positive and where f prime is negative. And wherever f prime is positive, that means f, the original function, is increasing there. And wherever f prime is negative, that means the function is decreasing there. Now remember, I'm using f prime to describe characteristics of the original function f. So make sure you understand the difference. Okay, so if f prime is positive, it doesn't necessarily mean that f prime itself is increasing. If f prime is positive, that means f is increasing. Okay, so we're going to start off by writing out each one of these factors up here. And then, of course, f prime of x. Okay, so now what you should notice is that the original function here, this is a polynomial function. Its domain is all real numbers. So amongst its entire domain, I want to find out where is f prime positive and negative. Now, how am I going to divide my intervals? Well, the zeros are going to help me divide up my interval. So what's the smallest zero I have? Which is negative 1. And then the next one is 0 and then 2. So my intervals, so if I were to write intervals, what's going to happen is my first interval is going to go from where? Negative infinity to negative 1. And see, I'm not including negative 1 because at negative 1, what do I know? My derivative is 0. So at that point, at that moment, your function is not increasing nor is it decreasing because the derivative is 0. Okay? But why do I stop at negative 1? Because at negative 1, I hit my first 0. Then I continue from negative 1. Not including negative 1, I'll go all the way until I hit my next 0, which is at 0. And then I continue from 0, and then I stop at 2. And then after 2, I've pretty much covered all of the zeros. So notice how this goes from negative infinity to infinity, which is the domain of the original function. So now let's make a sign chart. From negative infinity to negative 1 is 12x positive or negative. And as long as x is negative, 12 times the negative number will be negative. From negative infinity to negative 1, x minus 2 is also negative. And then from negative infinity to negative 1, x plus 1 is also negative. So then what am I finding? F prime is the product of these three, isn't it? Because there is f prime. So a negative times a negative is negative, times another negative, or sorry, a negative times a negative is positive, times another negative gives me a negative. Okay, so what do I know? From negative infinity to negative 1, f is decreasing. So I'll write f of x here, because remember, I'm using this information to talk about what f of x is doing. So from negative infinity to negative 1, my f prime is negative, which means f of x, that function itself, is decreasing. How about from negative 1 to 0? From negative 1 to 0, 12x is negative. Negative 1 to 0, x minus 2 is negative. And from negative 1 to 0, x plus 1 now becomes positive. So what do I have? A negative times a negative is positive, times a positive is positive, which, what does that mean about f prime? It is increasing. Okay? So then we go from 0 to 2. From 0 to 2, 12x is positive. From 0 to 2, x minus 2 is negative. And from 0 to 2, x plus 1 is positive. And so positive times a negative is negative, times a positive stays negative. So f of x is decreasing on that interval. And finally, 2 to infinity. 2 to infinity, 12x is positive, x minus 2 is positive, and x plus 1 is positive. So positive times positive times positive will be positive, which is increasing. So what do I know? F is decreasing from negative infinity to negative 1 and 0 to 2. And it's increasing from negative 1 to 0 and 2 to infinity. Okay? Now, let's move on to the first derivative test. Okay? So what's the first derivative test say? So the first derivative test, if you remember, we talked about finding potential maxes and mins. And if you remember, we said that, see, Fermat's theorem, once again going back to Fermat's theorem said, look, if you have a local max or min, and if the derivative exists, then your derivative at that value is 0. And then in class, we talked about, well, what if my derivative is 0? Are we guaranteed to have local maxes and mins? And the answer was no. But remember, we said those are all potential zeros. So the first derivative test is actually going to help me locate local maxes and mins. And the first thing we need to find are the critical numbers, which is where the derivative is 0 or undefined. So remember, just because the first derivative is 0 or undefined, it doesn't mean we're guaranteed to have a local max or a min, but that is a start. And then the first derivative kind of tells us what we could do further to figure out if we actually have a local max or a min. Okay, so let's write this out. So suppose that C is a critical number and what we mean by that is what? F prime of C equals to 0 or undefined. Of a continuous function f. Okay. So here's where the first derivative test kind of kicks in. So we know how to find critical numbers. But now we're saying, okay, is this critical number a max, a min, or neither? Okay, because remember, these are my potential maxes and mins, or they could not be. So here's what part A says. If f prime changes from positive to negative at C. Now look at what this is saying. In fact, you could probably complete the rest of this statement. Look, if f prime changes from positive to negative, what does that mean at my critical number? See, if f prime is positive, what does that mean about f? It's increasing. And then all of a sudden after C, f prime is negative, which means it's decreasing. So notice what you just captured. If f prime changes from positive, which means f is increasing, and then goes to negative, which means f is decreasing, you just captured a local maximum at C. So then f has a local maximum at C. So notice how, once again, f prime is being used to help me find local maxes and mins of f. So if f prime, if c is a critical number, which means my derivative is 0 or undefined. So before c, if f prime is positive, it's increasing. And then after c, if f prime is negative, it's decreasing, which means I have something that looks like this, which that's a local max. Okay, so f prime is positive, and then if this is c, then f prime is negative, and so I just captured a local max at c. Okay, now moving on to part B. And I'm sure this one you already know what's coming. So if f prime changes from negative to positive at C, so what do I know? F prime changes from negative. So if f prime is negative, that means it's decreasing. And then at C, after C, it changes to positive. Then I just captured a local minimum. So then F has a local minimum at C. Now, when do I know I don't have a local max or a min? I'm sure you've already guessed by now, if it doesn't change signs. So, and this is where our critical numbers are not maxes, nor are they mins. So if f prime does not change signs at C, that means it doesn't change from positive to negative or negative to positive, then f has no local max or minimum at C. All right, and so that's the first derivative test. Now, the first derivative test, the whole purpose of the first derivative test is to basically help us locate local maxes and mins, okay? And first we need to find our critical numbers, and so that's a start, but then just because we have critical numbers, we're not guaranteed to have local maxes and mins. It's practically, we have to run through this test. We have to pretty much make a sign chart again, right? Does f prime change from positive to negative, okay? So before we do our second example, and then we'll kind of stop there, I want to kind of define a monotonic function. Okay, so what is a monotonic function? So a function is called monotonic on an interval if it is either increasing or decreasing on the interval. So you could tell, I mean, we're talking about monotonic, so mono means it just does one thing. So on that interval, it's either only increasing or only decreasing, not both, okay? So, that's kind of what we're talking about here when we say monotonic function. So if I ask you, hey, is this function monotonic on this interval? I'm asking you, does it only increase or does it only decrease? If the answer is yes, then it is monotonic. If it does a little bit of both, then it's clearly not monotonic. So let's look at our second example, and then we'll stop there. So for example 2, find the local maximum and minimum values of the function g of x equals to x plus 2 sine of x on the interval 0 to 2 pi. Okay, so basically we've been given the domain, so we have to stay within 0 and 2 pi. And remember, I'm finding local maxes and minimum. So how is this different than the extreme values or when we found the global max and min? Remember, endpoints could be global maxes and mins, okay? But in this case, endpoints cannot be considered local maxes and mins. So the first thing I need to do is, obviously, we're going to use the first derivative test. So using first derivative test, we need to find our critical numbers. So as far as our critical numbers go, that you guys should be pretty good with. I know we've done quite a bit of that in section 1. So to find the critical numbers, I first need to find the derivative of g, which g prime of x would be what? 1 plus 2 cosine of x. And clearly I could see that 1 plus 2 cosine of x will never be undefined. So the only critical numbers I'll have is when this guy equals to 0. So if I set 1 plus 2 cosine of x equal to 0, and I isolate this, what will I get? I'll get 2 cosine of x equals to -1, which means cosine of x equals to -1/2, which now I could go ahead and look for my angles. And so sure enough, if cosine is -1/2, that means I'm going to land in quadrant 2 and quadrant 3 with a reference angle of 60 degrees, which means x equals to 2 pi over 3 and 4 pi over 3. Okay, so now that I found my critical numbers, now I want to make a sign chart again, kind of like what I did in example 1. So now remember, except in example 1, the domain of the function was all reals. This one is 0 to 2 pi. So, and one other comment I want to make is the reason why I picked 2 pi over 3 and 4 pi over 3 and I didn't go beyond these because of my domain restrictions. If I didn't have domain restrictions, there would be infinitely many. I'd basically have to say this plus 2 pi k and then this plus 2 pi k. Okay, so let's go ahead and make that sign chart that I did earlier. So we'll have intervals. And then what do I care about? My g prime. And notice how it's just this guy. I don't have any factors really. So it's just I want to know is g prime of x, which is equal to 1 plus 2 cosine of x, is this positive or negative? And once I know if g prime is positive or negative, then I could decide if g of x is increasing or decreasing. And then I could check or I could verify where my local maxes and mins are. So my first interval will start from where? It'll start from 0 and it'll end at 2 pi over 3, and then I'll continue from 2 pi over 3, and then I'll stop at 4 pi over 3, and then I'll continue from 4 pi over 3, and then I'll stop at 2 pi because those are my restrictions. So let's go through this. So 0 to 2 pi over 3, what do I see here? I could pick what? Pi over 2, right? Because pi over 2 is between 0 and 2 pi over 3. So if I plug in pi over 2 here, what do I know? Cosine of pi over 2 is 0. So I get 0 times 2, which is 0, plus 1. So that's 1, which means it's going to be positive. So what does that mean about g of x? From 0 to 2 pi over 3, g of x is increasing. Okay? So, and then what do I know? From 2 pi over 3 to 4 pi over 3, I could pick what? Pi to plug in here. So if I plug in pi, cosine of pi is -1. -1 times 2 is -2, plus 1 is -1. So what's more important is I get a negative number. So from 2 pi over 3 to 4 pi over 3, this is decreasing. And then finally, from 4 pi over 3 to 2 pi over 3, I could pick, for example, 5 pi over 3. Or I could pick even better than that. I could do something like something in the fourth quadrant, which why do I care about something in the fourth quadrant? Because in the fourth quadrant, cosine is positive. Positive times 2 is positive, plus 1, which will remain positive. So that's all I really care about. So you know that if you take anything in the fourth quadrant, that'll work out as well. So this guy is increasing. So now look at what we just found here. Over here, what do we notice? My function changed from increasing to decreasing, which means if it changes from increase to decrease, at the critical number of 2 pi over 3, we have a local maximum. So we could say local max at x equals to 2 pi over 3. Okay, now notice what happens here. This changes from decrease to increase when I change from 4 pi over, when I cross 4 pi over 3. So decrease to increase means we have a, if it's decreasing then increasing, I have a local minimum. So we have a local minimum at x equals to 4 pi over 3. Okay, so I'm not finished yet, because if you look at this example, the example says find the local maximum minimum values. All I've done so far is I found the location of them. So to find the local max and min value, all I really need to do is plug these guys into the original function, and then the y value will be the local maximum and local minimum value. So here's what we know. For the local max, I want g of 2 pi over 3, which g of 2 pi over 3 becomes 2 pi over 3 plus 2 sine of 2 pi over 3. And sine of 2 pi over 3 is just rad 3 over 2. So I get 2 pi over 3 plus 2 times rad 3 over 2, which becomes 2 pi over 3 plus rad 3. So that's my local maximum value. Now to find the local minimum value, I'll plug in g of 4 pi over 3. And that will be 4 pi over 3 plus 2 times sine of 4 pi over 3. And sine of 4 pi over 3 is negative rad 3 over 2. So this will be 4 pi over 3 plus 2 times negative rad 3 over 2, which then if I distribute the 2, I get 4 pi over 3 minus rad 3. And there's my local minimum. Okay, so if you, technically speaking, example 1 and example 2 were very, very similar, except for example 1, we kind of stopped where we talked about where it was increasing, decreasing, and so on. And in example 2, or after the first derivative test, we're saying, hey, look, by making this, we can do more than just say where a function is increasing or decreasing, because just by looking at this, I could tell where my local maxes and mins are. Okay, and so it's kind of like that's what the first derivative test does, which is just something a little extra than what we did for example 1. Okay, but the hard or the more complicated part or the time-consuming part was all of this. Finding your local maxes and mins, that just comes into play right afterwards. Okay, so that's not a difficult concept there. Okay, so that's where we're going to stop for today. And then next time we'll talk about kind of like, hey, what does the second derivative really do to this function? Or give us, what information does the second derivative give us about the original function? And then after that, eventually we'll be graphing really complicated looking functions pretty simply by just using the idea of derivatives. Okay, so that basically takes care of today.